Imagine a pristine industrial landscape, factories emitting only clean air, vehicles running on sunlight and hydrogen, and products designed to live infinite life cycles. But our reality looks like this. Heavy industry relies on combustion, venting massive amounts of pollution directly into the atmosphere to produce the materials we use every day. This diagram illustrates the sheer scale of the problem. Industry emits 8.6 billion tons of carbon dioxide annually, driven by processes that consume 40% of all global energy. Lowering those numbers often brings politicians and environmental scientists to mind. Yet the physical solutions to these problems, the turbines harvesting wind, the heat exchangers cutting energy waste, and the closed-loop manufacturing systems, are designed by mechanical engineers. The climate crisis has evolved past a policy debate. Redesigning the physical engines of society is a distinct mechanical engineering challenge. Let's look at the renewable energy sector. Modern offshore wind turbines are colossal structures, often standing taller than skyscrapers and operating in brutal marine environments. To extract maximum kinetic energy from variable offshore winds, these machines rely on complex pitch control mechanisms, automatically angling their massive blades with extreme precision to capture every possible gust. But they harbor a major life cycle flaw. While they generate clean power for decades, the fiberglass composites used in the blades have historically been impossible to recycle, ultimately destined for landfills. This animated diagram shows how Siemens Gamesa resolved that flaw with their recyclable blade technology. Engineers developed a novel resin bonding chemistry that dissolves under specific conditions, allowing the internal structural fibers to safely separate. Those separated fibers can then be recovered and reused in new manufacturing. True sustainability in renewable energy requires that the hardware used to harvest it operates in a completely closed loop. The transportation sector presents another massive target, currently accounting for roughly 12% of global carbon emissions. Inside electric vehicles, a quiet mechanical revolution is targeting every source of inefficiency. Engineers are replacing heavy steel with advanced aluminum alloys to drop vehicle weight, while designing complex thermal management systems that keep battery packs operating at ideal temperatures. Aerospace engineering takes this optimization further through digital twins. A digital twin is a virtual replica of a physical machine, updated by real-time sensors. In programs like Rolls-Royce's TotalCare, algorithms analyze over 70 distinct parameters per second per engine. This constant stream of data allows operators to adjust fuel mixture mid-flight and predict bearing failures weeks before physical symptoms appear. Over an entire global fleet, optimizing those continuous micro-adjustments prevents millions of tons of carbon dioxide from entering the atmosphere each year. By merging physical machines with predictive algorithms, routine maintenance becomes an active tool for reducing emissions. In manufacturing, the traditional linear model, where we extract materials, build a product, and eventually throw it away, is highly inefficient. The modern smart factory aims to close that loop entirely. This is BMW's assembly line in Leipzig, where the factory itself is a closed loop. Aluminum stamping scrap generated during production is immediately sorted, remelted, and reintroduced to the line, never leaving the factory floor. Engineers redesigned the pressing and sorting systems to achieve 99% material recovery. Remelting this scrap on-site requires 95% less energy than refining primary aluminum. Now look at steel production, one of the most carbon-intensive manufacturing processes on Earth. Heavy blast furnaces still depend heavily on coal-derived coke gas. At ArcelorMittal's Hamburg plant, a direct reduced iron furnace operates on green hydrogen. Hydrogen reacts with iron ore, exhausting only water vapor. Because hydrogen burns hotter, engineers completely redesigned the gas injection valves and internal heat management systems to handle the extreme temperature distribution. Decarbonizing an operation as primal and extreme as steelmaking proves a critical point. Every industrial sector can be engineered for a zero-emission future. Every blade resin reformulated, every kilogram of aluminum recirculated, Every watt of waste heat recovered acts as a tangible vote for a habitable planet. Transitioning global industry is an immense economic undertaking. By 2030, the green technology market is projected to reach $2.5 trillion. That capital is creating highly specific technical roles. Titles like digital twin specialist, hydrogen systems engineer, and circular economy consultant are rapidly moving from concept to high-demand careers. The physical infrastructure for the green transition is already under construction, and the demand for active participants is surging. The future relies entirely on the mechanical engineers building it today.